Hi everyone, I'm Arnab from Miston Labs, and I'm very happy to host this wonderful session on ZK, promising to be an excellent collection of talks, ranging from formal verification to new programming abstractions and verification of circuits. So to start off, a warm welcome to Alexander Hicks from Ethereum Foundation, who's going to talk about AI versus Q.
Yeah, thank you very much. I'll jump right into it. Maybe form verification and AI is a fairly hot topic at the moment, so I probably don't need to say too much in terms of grounding and introduce words, but we have AI now, which is really, really good. It's good for bad things like finding bugs, and it's good for really good things like finding bugs. And ideally, we want to kind of mitigate a lot of these bugs and not just find them, whether they're good or bad. And the best way to do that is form verification, and we get proofs, QED, up to obviously a set of explicit assumptions. And so we're going to kind of look a bit at what this means, not just for verification, but actually I'm really going to talk about software engineering more than anything. So one motivating thing to look at is the straw map that we have for the EF. This is a fairly big straw map. We've got a lot of items on there, and a lot of these things are cryptographic in nature. So there's quite a lot of ZK, there's a lot of migration to post-quantum cryptography, and there's a lot of things to cover. And we have to cover quite a lot of these things in a fairly short amount of time. If we're thinking that maybe quantum computers break elliptic curve cryptography by 2029, 2030, we're going to have to speed up our migration. And in the ZK case, Aztec and Zcash, which are probably the two teams with the most experience and competence in deploying ZK, still have pretty disastrous bugs that happen in their stack, even after years and years of experience. And this feels like a problem that's maybe not just a competence problem on our end because people are pretty smart, but also maybe a tooling problem, and maybe we have to find better ways of actually doing things and deploying these things to actually deploy them safely and at scale with good performance and all the things that we actually expect. And in particular for Ethereum, we want to avoid the need for any kind of social governance intervention if there are disastrous issues. We had the DAO hack many, many years ago. We've managed to avoid such things again. And so it's pretty important that we try to do the whole way and get end-to-end form verification of some kind to really mitigate the risk of bugs entirely and remove our needs to intervene and kind of, I suppose, in some way compromise the ideals of blockchains that we're all building. So ZK VMs, I think, are a pretty good model to look at because it's a fairly interesting stack. It covers a lot of the software. It also covers some interesting mathematics on the cryptography side. If you haven't seen ZK VMs before, there's a simple way to think of it. You have a guest program, let's say the an Ethereum execution client or the STF. You're going to compile this to a ZK virtual machine. Let's say that that's a RISC-V VM, and it's ZK in the sense that the semantics of RISC-V are meant to be arithmetized and encoded into a set of polynomial constraints, such that when you have an execution trace of your guest program being executed in that ZK VM, you're going to be able to produce a witness from it, and that's going to allow you to prove something about the computation that you've done on the ZK VM. You're going to get a proof, you're going to verify it on the L1, and for example, we can scale the L1 to endless levels of scalability with this because proof verification is fairly short, and proof production obviously scales fairly well with GPUs and performance engineering, and it's only getting better and better. But we need to be able to deploy this safely. If you want to deploy this safely, here's a kind of basic diagram that gives you an overview of all the things that you might want to prove. So if you start from the guest program, that's going to have a specification. You want to ensure that that guest program conforms to that spec so that you're actually proving something about the guest program that you assume you're proving something about. That guest program obviously gets compiled to your ISA. You want to maybe worry about the compiler a bit and make sure that the compiler is not going to change the semantics of your guest program. And then once you have your ISA, you have obviously the constraints, you have the witness generator. You both want to show that the constraints are sound and complete in the sense that satisfying the constraints implies some execution of the ISA or some program in the ISA language, and then obviously that for every execution of the ISA language, you have a corresponding witness that's going to satisfy the constraints. And you want witness generation constraints to be consistent in some sense so that essentially you can always ensure that the witness for any valid execution of a program is going to materialize itself and satisfy the constraints and allow you to prove them. So then, again, you have a spec, which is your ISA spec. Let's take RISC-V as an example, and we have kind of RISC-V failed that extracts the lien. Similarly, again, for precompiles, these are just handwritten circuits. They're there for performance. You have a functional specification for these. You want to show conformance. And then again, for the proof system, you have specs of some kind which are formal. Luckily, we have provable security for ZK, which is very helpful in validating our specs. And again, you're going to try to show something about the implementation of your prover and your verifier, whether that being kind of CPU or GPU code, to be able to show that you're going to get, again, soundness, completeness, and all of this. And the same for the recursion, where the verifier is implemented in circuit, and you're mixing a bit of constrained verification with, obviously, spec compliance for the verifier. I think this is not particularly new. It's essentially just a checklist of things to verify. And it's fairly interesting, but not the main topic of the talk. But it's there for grounding, and it's fairly important to really keep in mind what we actually want to show about these things and maybe some of the complexity in this. So if we look at how we actually do this in practice, the easy way to do it, or the kind of a straightforward way to do it, is to look at what we already have implemented. Typically, this is in Rust. And then to look at what specs we have. So for something like the RISC-V ISA, there's an official sales specification of RISC-V. And then we try to get both into a proof assistant. In this case, it's going to be lean. I'm sure the talk is going to be lean. But it could be something else. And then once you have everything in lean, you can do some proofs. And so we have some example proofs for SP1, for OpenVM, for Pico. There's some ongoing effort for Zisk, which are all kind of ZK VMs, which are at a cutting edge of performance. And we've been able, with kind of both SP1 and OpenVM doing some in-house work, Nethermind as external contributors and things like this, to do, to show at least soundness of the constraints, which is some good level of assurance. We also have some example proofs for some precompiles. And this is going fairly well. But there's an interesting thing that starts to look like, which is that we have to get everything into lean. And I'm going to come back to this again and again in the next couple of slides. And this is rather annoying because one, it's extra effort, right? There's one more thing to do that doesn't actually involve proving anything at that point. But also, this is very trusted. So if you extract Rust to lean in any sense, in the case of the constraints, you're just passing constraints off of the Rust AST. One, what you get is like a bunch of SSA values from the compiler. So it's not very structured, and it's not very pretty to look at or easy to reason about, which is a bit of a hassle. But also, it's completely trusted. Rust has no formal semantics, and so you can't really prove anything about your extraction of Rust. And so, and then obviously, your parser for the constraints is trusted and so on and so forth. There's basically quite a lot of trusted code base in there, and that has to be validated, and because it has to be validated without doing proofs, you can't just, AI everything, which is rather annoying in this kind of day and age. So one takeaway is like, yes, we can do proofs. We have, a good track record of doing proofs. We have actually several talks online that you can find where we go over, in an hour of the technical aspects of doing these proofs. But there's a bit of churn, which is kind of getting everything into lean in the first place. The same pattern kind of shows up if you try to say something about the guest program. If you look at the case of Ethereum, you have a bunch of guest programs that could be written in C++, in Go, in Java, in Rust, in NIM, in Zig, in C#. Pretty much all these language, again, no formal semantics. And also the state of their compiler to RISC-V is maybe not as mature as a compiler to x86 or compiler to ARM that are more frequently used. And so there's a high chance of bugs for all of this. It's also quite hard to come up with a uniform way of verifying maybe the different guest programs in this sense, because they all have very, very varying levels of tooling to support form verification and extraction to lean. So Rust is fairly mature in this sense. You have things like hacks and Aeneas that extract Rust to lean. But for Java, Go, NIM, things like this, I'm not really aware of anything good. C++ maybe has a track record of form verification, but it's memory unsafe and it's very annoying to do. And you might verify the source code, and then you're still trusting some compiler to RISC-V, which is maybe less mature. In the early days, we had people doing kind of custom, RISC-V compiler targets, which was maybe not great. And so again, it's kind of like, yes, we can kind of do things, but it's rather annoying. There's a lot of trusted code. It's hard to get kind of really end-to-end assurances that we would like to get, because again, we're trying to really reduce the chances of bugs to 0, because we're trying to do a blockchain here, and we're trying to not have the need for human intervention when things go terribly wrong. Cryptography story is kind of similar, but it's starting to look a bit better already. So again, what you're going to start with is Rust implementations, where a lot of the nice cryptography is implemented. It's nice, it's fast, it runs in production already. It is somewhat safe. There are bugs that happen, but mostly speaking, it's not a complete disaster. And luckily, obviously, with all the ZK stuff, we have provable security, and so we can state specifications in a library like arclib, which we have, which is supported by a bunch of different libraries as well. And these specs can be executable. They can have proven theorems about them in terms of soundness and things like this. You can do fry, you can do whir, you can do binius, sumcheck, all of the protocols that you kind of want to do, you're able to do there, and you're able to get an executable spec, and you can validate it. And if you extract your Rust code into Lean via Hacks or Aeneas, then you can maybe verify your Rust code. Again, there's this caveat, which is this kind of trusted code base. And we've seen in some papers recently, kind of by Nadeem, that sometimes you have bugs in this sense. The translation has to be validated. It's not always clear, at the edge cases, things like this. But also, there are a lot of difficulties. There's a lot of Rust code in something like Ponky3, which a lot of people use, which simply does not extract at all, because it uses a lot of patterns in Rust code which are not supported by any of these extraction tools. And obviously, validating a set of semantics for these would be very hard and quite a lot of effort and take quite a lot of time. But if you're doing, returning mutable borrows, having a lot of custom trades, a lot of nested iterators, and things of this kind, there's a lot of limitations there. And we've essentially been unable to extract large enough amounts of Rust code to Lean from ZKVM crates for this to feel like a very good way of doing things. You might have other options. One option is obviously you're starting from specs which are executable in Lean, so maybe you could just compile this and think about running this. And this could be you write a compiler, maybe you look at MLIR, there's a formalization of MLI in Lean that I'll get to in a second, or maybe for a verifier or kind of small program, you could consider just writing assembly and skipping any issues about the compiler and verifying source code, and obviously just verifying this assembly in Lean. But yeah, same story as usual. There's a bit of frustration, which is there's a lot of trusted code, there's a lot of tool chains, there's a lot of things which are kind of hard to maintain, right? And so right now we're at the state where we have a bunch of proofs. We are kind of happy that these proofs are fine in the sense that okay, we trust Lean, we trust the Lean kernel and things like this. We trust our specs, let's say the RISC-V specs, at least they're kind of canonical in some sense. They're provided by the RISC-V Foundation. We're not inventing these things ourselves. For ZK, we can kind of prove some things about our specs. Obviously, there's things like Fiat Jamais, where we can, it's not exactly provably secure, but we can have some confidence in our specs and so on. But we're trusting a lot of extractions and additional assumptions, not extractions, but more assumptions, which we have to trust. And we found issues in existing efforts to fully verify things where some assumptions were invalid. For example, with respect to the RISC-V spec, if you assume 4-byte alignment instead of 2-byte alignment or something like this, as well as stupid little mistakes like making two assumptions which together amount to assuming false, and then you can prove whatever you want from assuming false. So even if we have proofs in Lean, it's not entirely satisfactory in that sense. We're not exactly kind of as confident as we'd like to be that these proofs are as good as they should be. And also, we have proofs primarily for individual components and maybe not for a full end-to-end ZKVM. And there can be issues with interfaces, with APIs, with kind of glue code beyond the individual components, which we'd like to try and address. And even beyond this, we obviously have some issues, I think, in terms of having, kind of high-quality software engineering practices, which is considering, the cost of form verification, making it sustainable and repeatable because all of this code is live, and then things like maintenance and CI integration, the robustness of the proofs that they don't break on every commit, and of course, keeping track of our verification boundaries, which for something like a ZKVM is quite a large stack and has a lot of boundaries potentially if you're just looking at components individually one by one. This is kind of usually where the talk ends if you go back a couple months. And I would have said a bit more detail about how we verified this or that and so on. But the aim of this talk is to try to be a bit more future-looking and to maybe say, spend a bit less time on what we've already done and spend a bit more time on how I think we are going to do things moving forward. The motivation for this is that ultimately, when we talk about form verification, correctness is something that we really, really want, and we want security, and we want all of these things. But fundamentally, to deploy software, it has to be fast, and it has to be pretty decent quality software to want to deploy it, aside from any correctness issues. This is this blog post from AWS from 2024. I have basically linked to it in every talk I have done since that blog post has come out. And the point of that blog post is essentially that, at least at AWS, the experience is that they've put a lot of effort over the last maybe 10 years into putting formal methods into their development process for software. And they feel like they've had better experience developing software as a result, in the sense that they develop software faster, and they feel that it's higher quality, and they feel that it's fast and it's kind of more performant. which is really, really good. And I think ultimately what we want, much more beyond correctness, and a very nice way to kind of justify investment in formal methods, beyond this kind of correctness thing, where performance is often more of a blocker to shipping code than shipping broken code, since a lot of broken code does get shipped, and a lot of snow code, not so much. So this is 2024, and things have kind of, changed since then, primarily because AI has gotten really, really good. And not only has AI gotten really, really good, but Lean has gotten really, really good as well. Not just as a proof assistant, but increasingly as a programming language. And so what I want to focus on for kind of this part of the talk and the future-looking part of the talk is the idea that maybe we should actually just, scrap everything, delete all the software ever written in the world, and just do it all in Lean. This is an opinion to take. Not everyone at EF necessarily agrees with this yet. They will probably agree with this by the end of the year. But in practice, actually, we think about a ZKVM, we can kind of do this already. And actually, I can say that we are actually doing this already, and hopefully, we'll be able to report back positively about this within kind of a month or two and have basically a ZKVM model in Lean. And what I mean by this is that we have a guest program in the form of EVM ASM. EVM ASM is basically an attempt to use Lean as a macro assembler. And so we have Claude, or multiple instances of Claude and Codex and other open source Chinese models running 24/7, writing an EVM implementation, or write actually the full Ethereum state transition function in raw RISC-V assembly, verified in Lean. And it's really quite interesting. The reason that it's interesting is, one, obviously, we're just generating raw assembly. We can also verify our code generation from Lean. So we have high guarantees in terms of, this is secure and safe, and it conforms to a spec. And it's, ongoing work, but it's going pretty well. And we're kind of hoping that by October, it's something that you can actually run and integrate with a, proper full Ethereum client. But also, there's a performance angle to this, which is that you're writing raw assembly, you're writing it with AI, and you can obviously profile your assembly against the Zisk emulator or some other ZKVM emulator, and you can identify where you find performance boost, which you would not find with a stock compiler, because stock compilers are meant for RISC-V hardware in terms of their target, and ZKVMs have got a different performance profile. There's some literature out there on this, but you pay for things like branching in a way that you don't for hardware, so on and so forth. And actually, even different ZKVMs have their own performance profiles. And if you're just outputting raw assembly with, Claude or Codex or something else, you can kind of give it hints, and you can even do profiling, and you can do things like take the last 100, Ethereum blocks and look at what's in the transactions and optimize different instructions for this. One example would be division. If you do the division opcode, you can have implementations which are faster with small divisors. You can have implementations which are faster with large divisors. I took the last 50 Ethereum blocks, did some profiling. It seems that for DeFi, you see a lot of small divisors, so you can pick an implementation for that opcode that is optimized to what you see in transactions in Ethereum blocks and get optimal RISC-V assembly for your use case, which you can then tweak for every ZKVM. This is pretty good. We don't really have full benchmarks numbers yet, but basically I'm assuming that by October we will have the fastest STF that people can produce, because we will be able to really fine-tune everything based on profiling and with kind of direct feedback loops and high assurance in the sense that we have lean theorems, both in terms of compliance with the SAIL RISC-V model and obviously with an Ethereum spec. So we should be good with that. Again, kind of similar story with Clean. Clean is this circuit DSL, or kind of constrained DSL that was developed by ZK Security with a grant from the EF originally. I think Zcash now also use it. There are other use cases for it that I encourage everyone to use it. And again, you can kind of just write your constraints in Lean. And the nice thing is then actually proving that your constraints are correct in terms of soundness and completeness is about 10 to 100x easier than if you take the extracted constraints. A very easy way to think about this is that if you're extracting from Rust, you're maybe going to get, 30,000 lines of Rust compiler, SSA stuff. In Clean, you're going to have a nice little Lean function that generates your constraints, and you're going to have a 10-line proof that is, sound for a Kachak permutation, and then you just stick all the Kachak permutations together, and it's 70 lines to stick them all together, and that's it. So this is really, really nice. And again, once you have some theorems, you can optimize your constraints, and we'll see a very clear example of this in a second. Once you have the constraints and you have the guest program, you need a proven verifier. And for this, we have RClib. So RClib is this library of arguments of knowledge. We have a full frame, kind of foundational framework based on interactive operator reductions. And we can write down specs for our proof systems. There's some check, there's try, words coming very soon, Binius is there. Whatever you want, you can kind of add as a spec. It's a bit of churn still to add things like specs, but we can make them executable. We can obviously prove things about them. and whether we verify implementations in Rust against them, or ideally, because I'm really pitching to do it all in Lean, generate fast code from Arclib itself, either way via the native Lean compiler or via a custom compiler, then we should be able to actually just have verified code generation in some sense. And this could even be generate Rust code that is constrained to extract back to Lean with AI instead of relying on current Rust implementations, and then again kind of having a feedback loop that makes it fast. And if you really, really want to have even more performance, and you think, I really want a custom compiler, I want GPU backends, there's an implementation of MLIR in Lean. It has verified data structures. You can already start building on this now. I was asked by the maintainers of this to specify that it is obviously an early project, somewhat work in progress, but it's pretty sick. And I'll kind of briefly say that some of the data structures there are verified and faster than MLIR C++, which is pretty incredible. And a good indicator that even kind of native Lean performance can actually be competitive with things like C++ and Rust. There was a blog post from 2 days ago, someone wrote a compression library in Lean, which is faster than a pure Rust one on some inputs. So we're really seeing kind of performance comes through for a lot of actual programs. And not even withstanding just, write compilers, have GPU backends, optimize them all. Now, why do I think that this is going to yield really incredible performance beyond just what people are doing now? The reason is that if you take this stack and you kind of, basically put in these Lean libraries instead of a bunch of Rust code and things like this, you can start thinking about auto research. I think this was shown yesterday in another talk, so maybe there's some context that I need to go over, but Google were like, okay, we're not going to publish our circuits, and then Eigenlabs set out to them, we're like, okay, let's just auto research this and let's do better than them, and we've seen incredible results. And people have kind of latched onto this. And we've seen things like ZK Golf, which is an initiative by ZK Security, who maintain Clean, to try to optimize their circuits using an auto research pipeline. This is an example of a challenge that they released yesterday, which is doing SHA-256 compression over binary fields. Please go to the Flock talk tomorrow to learn about binary fields, since they're going to be very cool. And I have a very nice story about how simple it is to optimize things, and you can see this is optimized beyond Flock already, as of kind of yesterday, which is that I saw the challenge when I was about 20 minutes away from leaving my hotel to go and give a talk at Axiom down the road on University Avenue. I came up with some target optimizations. I fed them to Claude. I go to Axiom. I give them actually this talk, but this slide had, at the time, another ZK Golf challenge. And I promised during my talk at Axiom that by the end of my talk, I would have kind of been on the top of the leaderboard. And this is this first little point here, which is me beating Flock whilst I'm giving a talk at Axiom and getting a big improvement. And so I was then not top of the leaderboard. So yesterday at 1 a.m., I made sure that I would be top of the leaderboard to take this screenshot. I've since been beaten again. But basically, you can just kind of throw challenges like this, and people will come and essentially do kind of citizen science of optimizing everything that you could want, using their Claude subscriptions, their insights. And same as ECDSA.fail is just like one big Telegram group of people enthusiastically contributing and making things fast. It seems fairly obvious that as long as you can specify some correctness theorem for your code in Lean, and you can specify some cost model over which to optimize, you can basically do this for the entire stack. If you think of EVM ASM, we have different EVM opcodes. We can show that they comply with the EVM spec. We can show that they are valid RISC-V code. And then for every opcode, we can just auto-research it against some cost model that can be ZKVM specific. If you think of things like Clean, we already had an example here, so I don't need to go over this more, but there are many more examples on zk.golf. And then if you think of Arclib, it's kind of the same thing. And let's think about Arclib and think about cryptography. We have an open problem, which is that there are these conjectures about proximity gaps. The EF has put up $1 million to try to resolve these. There's been a lot of activity, a lot of interest, and I'm happy to say that the proximity gaps kind of paper that Dan and others have produced and put on ePrint, I formalized this in Lean. It's going to get merged into Arclib very, very soon. I just need to basically split up the PRs to make merging a bit easier. And I have a repository already set up to accept submissions to try and resolve these conjectures with auto research. The $1 million prize doesn't get split up between some prize for the kind of traditional, nice, polished pen and paper proof that has to go through an academic peer review process. And then the other part of the prize is going to be for just do it in Lean, however you want, with auto research, with insights, whatever, doesn't matter. And I'm fairly enthusiastic that this is going to be resolved in a very nice way, maybe soon. And so please warm up your GPUs, and this will be live very soon, as soon as I actually set up a website to get submissions. But all the lean stuff is there. It's ready to be received, and I'm very much looking forward to try to make this fast. And even beyond that, I think this will only be a first step. And I anticipate that maybe by the end of the year, if I can make a prediction, we will have auto-researched maybe a new IOP for some interesting statements like batch Boolean computations that will very possibly, I hope, be faster than what we already have. So I feel like this is a very interesting way to think about development now, which is that for form factoring, we've always gone on about, correct by construction code and all this stuff. But now we can really think about, like, let's write specs. Let's maybe write some components from the specs. And let's actually just do kind of provably sound optimizations of all of our code with auto research, with people contributing. And this is very, very fun, I think, as a process, because people can get involved, people can contribute. It feels very open source. It feels very kind of joyful as a community effort. And I think there's also then interesting things. So if you do mechanism design, I think there were genuinely interesting problems in trying to think about this through the lens of mechanism design to encourage collaboration, to encourage coordination, to encourage efficient use of everyone's compute. And this seems like very exciting. That's what I want to get across. I'm very hopeful that maybe this will impress on some of you to pick up lean, use AI, and try to make things fast and sound and secure. And we can maybe have better software very soon by the end of the year. Thank you.
Very exciting direction. Any questions? Maybe just one in the interest of time.
So I'm curious in this effort to convert everything to lean. There are projects to try to automate the conversion of C++ to lean.
Yep.
Do you think those are worthwhile, or do they end up just generating lots of unsafe code?
I think yes. I think the downsides are that when you convert things to lean, so I mean, either you convert it with AI and just port this over to lean, and then it's kind of where's it at support or where's it just writing lean from scratch. It doesn't really make a difference for me. Or you're converting it in a kind of deterministic way, in a way that's maybe traditionally done also for Rust. And then the thing there is does the lean look nice? And does it look like something you want to maintain? It depends a lot as well, just in the sense that typically you do this to then verify your lean model of your C++ or Rust code, and then you assume that your lean code is representative of your C++ code, and then you assume that therefore your proofs about that lean model say something about your C++ code. But if you're just running the lean code, then you probably want lean code that maybe looks nicer, that also forms a broader kind of code base and not single functions. And so I think you're better off maybe just rewriting from scratch. And rewriting and refactoring now is very, very cheap, right? We can refactor, even in our clip, we can I don't know, we generalize linear codes to module codes so that interleaved codes and linear codes are both instantiations of module codes. And this is kind of, you write down the definition, you give it to Claude, it refactors the library, it fixes all the proofs. It's very, very quick. And actually, it then actually goes downstream to other things, which is that Giacomo took the Zook paper and was please do this over module codes, looking at the lean thing, and it worked, right? So I think right now, historically, we were concerned of how do we make contact with things in production in C++ and Rust. And now I'm really thinking if we can just write it in lean and then auto research it. And the point about this auto research thing is this is one day. The slides are gone, but it's 1 day to find something optimal. And I haven't done this for this, but for the other SHA-256, I have impossibility results that for all known sets of optimizations, they can't be generalized further. So we have a sense that unless you find a completely new class of optimizations around bitwise operations, this is as optimal as it's going to get. And so then why would you bother thinking about your old C++ code that you can't really optimize in that way, right? So it's really, I'm really saying let's just kind of, obviously not delete everything today, but progressively, I think we should really consider just rewriting things in lean, and it can be really, really fast. I mean, this EVM ASM is a full Ethereum STF, and I think we'll basically have something that is maybe faster than the rest, and it kind of runs and integrates in the client, and it'll be a 5 months effort as us doing this for the first time, which is faster than any Ethereum STF probably took to develop. And this is kind of one person full time, one person part time, me looking at it once a week, and Claude's not an insane cost relative to the cost of engineers.
Thank you, Alexander.